When solving a radical equation, the two things we want to keep in mind the most are to first isolate the radical. That means we want the radical alone on one side of the equation. And after isolating the radical, we can raise both sides to a power. We're going to choose the power that will clear the radical. Generally, that means we're matching the index of the root. So in this example here, our radical is the cube root of 2x minus 1. The first thing we have to do is isolate that. We have a plus 3 on the same side. We're going to stick with simple ideas here and just subtract 3 from both sides. So that gets us the cube root of 2x minus 1 on the left, and negative 2 minus 3 is negative 5 on the right. Now, because the index of the radical is 3, I'm going to raise both sides of this equation to the power 3. So I'm cubing both sides of the equation. On the left-hand side, the index of the radical and the power undo each other, right? If we have a cube root raised to the power 3, what we get back is what was inside. So we're left with just 2x minus 1. On the right-hand side, I just have to cube negative 5, which gets me negative 125. Now I have a very simple linear equation. So this could turn into something linear, it could turn into something quadratic. We just need to wait and see what we have as a result of applying this power and go from there. So very simple linear equation, add 1 to both sides. Divide both sides by 2, and we're done, right? So we get that x is equal to negative 62. So our solution set is just the value negative 62. And just like with any equation, we can check this by plugging it back in for x. A very important thing to keep in mind when we're doing this check is that we plug into the original equation. We never take the equation after doing any steps, like after clearing the radical, for example. And all we do is evaluate both sides to see if we get a true statement. So this gets me the cube root of negative 125 on the left-hand side, plus 3 equals, and we're still looking at this with a question mark over it to see if it's true. This turns into negative 5 plus 3 equals negative 2, which of course we can verify is a true statement. So checking our answers helps to build some confidence that we did a problem correctly, and it often also helps us to understand the solution just a little bit better. Here we have a word problem involving a radical equation. So we're told that the weight, average weight for men in pounds can be estimated by this formula that takes into account their height in inches. So we're asked to find the men's height that corresponds to an average weight of 180 pounds, so this is a value of W. We have here a graph. We can relate this to the power functions because this power is greater than 1. So notice that we're looking at a power that is greater than 1. And note that our graph has that upward arcing curve. It's concave up. So that's consistent with what we have observed about power functions. Here's a value of W. We can trace over on the graph to estimate this. And from our estimate, it looks awfully close to 75, so we'll start with that initial guess, but we'll use the formula itself to actually verify. So plugging in 180 for W, we're going to follow the idea of isolating the radical first and then raising both sides to a power. So my radical in this case is h to the power 1.7. because that power is fractional, right? It's a decimal, but that is the same thing as 17/10, so that is a fractional power. This is a radical expression, and I can isolate it by dividing both sides by 0.1166. So bringing in a calculator for this, we get 180 divided by 0.1166, and that's 1543. I'm going to put several decimal places down here because I'm not done with this computation. So I'm going to choose to write this as 1543.739. I think 0.739 should be sufficient. Now the power that's going to clear the radical in this case is the reciprocal of the power we've got. Since I know this power is 17/10, I could think of it as raising both sides to the power 10/17, but it works to be a little bit sloppy about it too. Since we're going to get the calculator to do the main work, I'm just going to raise this to the power 1/1.7. Since all we need is a decimal approximation of our answer, this is going to be just fine. So I'm going to now bring that calculator over again. I still have the number entered. I'm going to just raise it to the power. I need to use parentheses for this. 1 divided by 1.7, and then close the parentheses on that power. So I get 75.098. Let's call that 75.1. Because we're asked to round our answer to one decimal place. So we will say that the height that corresponds to an average weight of 180 pounds is 75.1 inches. So that's about 6'3". That idea of a reciprocal power that we applied in the last example is helpful, but it can be a little bit dangerous. In this case here, because the numerator of this power is even, I'm going to put this in radical form instead and start to solve it that way. And we'll see why by the end of this problem it might have been a good idea to do that. So I'm going to rewrite this as the cube root of x minus 5 quantity squared is equal to 4. And to clear just the radical now, I'm going to cube both sides. What that gives me is just x minus 5 squared on the left, and 4 cubed is 64 on the right. Now I have an equation that's really well set up for the square root property. I can take the square root of both sides, considering, of course, the plus and minus square roots as I do that. So that this becomes x minus 5 equals plus or minus 8. And if I add 5 to both sides now, I get that x is equal to 5 plus or minus 8, which I can now break up into the two separate cases. 5 plus 8 is 13, and 5 minus 8 is negative 3. So I have two solutions to this equation. If I had applied that reciprocal power, x minus 5 to the 2/3, take both sides to the power 3/2, it could still work, but I would have to be careful with the implied square root here. I would need to consider both the positive and negative square roots. And it's a lot harder to recognize that you need to consider that in this form than it is in this form. So I think that in a situation like this, or really anytime you're uncertain, it's safer to go ahead and just clear the denominator of that power first, and then work with whatever polynomial equation that gives you in the next step. And we have saved our hardest equation for last. It doesn't look hard, but it does turn out to be a little bit more involved than the other ones. I'm again going to start by isolating the radical, which I'll do by subtracting 3 from both sides of the equation. That gives me the square root of x minus 1 equals x minus 3. I now go ahead and square both sides in order to clear the radical. And that gives me x minus 1 on the left. And I have to square this out as a binomial. Remember that we get 3 terms. Sometimes in the context of a longer problem, people oversimplify the squaring of a binomial, right? We're not allowed to just square x and square 3. We have to square this as a binomial, which gets us x squared minus 6x plus 9. In case you're not seeing right away how that works, I've put a little calculation over to the side here that you can refer to, where we just write x minus 3 times itself and FOIL it. So we now have a quadratic equation that we're going to solve for x. It seems like factoring is worth trying, so let's go ahead and get all the terms on one side. I'm going to do that by subtracting x and adding 1 to both sides. And that makes everything go from the left, so this is now 0. And on the right I have x squared minus 7x plus 10. This factors as x minus 2, x minus 5. And so I appear to get 2 solutions. I'm going to go ahead and check these now, each of them individually, plugging in 2 and plugging in 5. You can pause the video and try it on your own and see if your answers agree with mine. Setting both of these up, I just want to go to the original equation and plug in the solution. This first one gives me 2 minus 1 is 1, square root of 1 is 1. So this gives me the statement 4 equals 2. This is not a true statement. The second one gives me 5 minus 1 is 4, and the square root of 4 is 2. So this one gives me 5 equals 5, which is a true statement. So coming back to my solutions now, I'm going to not accept x equals 2, but accept x equals 5, which did pass the check. This 2 here is what we would call an extraneous solution. And an extraneous solution is a solution that comes about through the normal process of solving an equation but doesn't satisfy the original equation. The step that brings it is this one right here when we square both sides. When you square both sides of an equation, you lose a little bit of information. The information we lose in this case is whether each of those expressions was positive or negative before squaring, because everything becomes positive after squaring. One way to see what the extraneous solutions are graphically is to just go ahead and graph both sides of this equation. So we can take a look at that. We'll graph these in Desmos, but realize that these are functions that we absolutely know how to graph. This is just a square root graph shifted right 1 and shifted up 3. So we'll recognize that graph when we see it. And on the right hand side we have just the graph y equals x, which is a straight line passing through the origin with slope 1. So let's just take a moment to graph those now. Here in Desmos I have graphed the left and right sides of this equation, And we can see the correct solution at 5, 5. This is our extraneous solution down here at 2, 2. And we can see what it really is by letting this other part of the graph show up. The bottom half of that parabola, which we would get by putting a minus in front of the square root, intersects with the line there. So that extraneous solution comes in from the fact that we have only the positive square root, not both the positive and negative square roots, in our original equation. So remember that the meaning of this square root symbol, we tend to just call it square root, but the meaning is actually principal square root. It means only the positive one, even though both a positive and a negative square root exist.